please join me in welcoming Professor Reinhold Scherer of Essex University.
Very much and no pressure. See if this works. So yeah, again, thank you so much for having me back. Last time when I was here in October, I think, I presented what my work was in the past 20 years. And today I go a little bit outside of my comfort zone, and I would like to show you what we plan to do in the next 20 years and what we already started to do. And the title, it has to do with breakthrough interfaces to some extent, but the title today is Biohybrid Platform for Synthetic Biological Intelligence. And hopefully by the end of this talk, if you don't know these concepts, it somehow makes sense and you understand what we try to do. And you agree that there's a lot of potential. Of course, this is not just my work. I have the pleasure to be here, but I have a couple of people in the lab who are working hard to make this possible.
No. Okay. The clicker doesn't work. Oh, it doesn't seem to work. Don't worry.
This is not my batteries. Anyway, let's. Oh. Slide what two? Okay. It was so let's start with we already had a conversation before. Let's start about artificial intelligence or talk about artificial intelligence. Someone heard already about artificial intelligence in this room?
Yeah. On the grapevine.
What do you expect from artificial intelligence? This is just a warm-up exercise so that
at present, not a measure.
Human capability, Skynet.
Okay. Some people watch a lot of TV. Someone else wants to. So what do you expect?
Automation. Human capability.
Human capability.
Predictions based on history.
Perfect. So I guess
Heuristic.
I know I asked ChatGPT because I guess it enhanced my quality of life now. Be honest. So of course it's about human augmenting human abilities, decision making. If you've seen some research, I guess this year, last week, was showing that maybe it's not really assisting, but it's more outsourcing. And again, the brain or the muscle or the body, if we don't use specific parts, yeah, we lose this part. Again, it's definitely helping. It helps us solve complex problems. It drives innovation. So there's a lot of benefits. A very powerful tool, which we all use it. It's really, really powerful. Now, what is the definition of AI? There are many definitions out there. Today, I picked this one. Every time I try to pick a different definition. But at the end, it always it's always about there are some objectives which we either have to state explicitly or implicitly, and then the machine somehow with predictions, which we had before, content recommendations, decisions which again have an impact in the real world or in the virtual world. But again, you will find a lot of different definitions, but it's always about creating, testing something new. Origins. What if this might be a little bit boring? I just try to explain you. I hope after all of this, you see where I want to go. But it's not so old. I mean, it started really a big boom in the 50s of the last millennium, not even 100 years ago. With Alan Turing, who tried to understand is machine intelligence, and only then the term was coined. So it's really a young field. And then in the 60s, 70s, there was this big explosion of expert system, all the hopes in AI. And then also the first neural networks came up, and the human brain, the circle starts to close, served as an example, as a template on how to play it. And then in the 80s, reality kicked in, all the hopes were unmet. But then again, with the advancement of methods and better technology, suddenly in the 90s, the machines improved. And again, IBM's and Deep Blue was the first machine who really beat a chess player, a human chess player in chess player. And then based on that, the boom started. And nowadays, everything, including your toaster, probably has a lot of AI in it. Whether needed or not, but that's my take. So this is where it came from. But now the question is why the brain as an inspiration. You know? If we look at the characteristics of the brain, it can do really complex processing of what we do. It's really amazing in learning, adapting. You think about how many tries. I mean, it takes some time to develop. If you think back when you were a kid, you can use your hand in a very dexterous way. It probably takes a lot of learning, years probably. But then once it's learned, you can really quickly adapt. You can drive a car, you can ride a bike, you can do many amazing things. So you can really learn quickly from experience. It's a big parallel processor. It's not one single thread, but many. And another really great skill over the brain is really skilled is pattern recognition. So if you see someone moving, you don't need to see the person, you probably already know who's coming. So it's really developed a lot of skills, which we are really fascinated by, and we want to modern machines at the end. Now, how does the brain work? The brain consists of a big network of different cells. Okay. The most important type of cell is the neuron. Maybe you heard about it. Neurons are special cells, and they are the only cells who can actively transport information and also manipulate information. Then we have different cells like the astrocytes. The astrocytes provide nutrients. They are the babysitter of the neurons, but also they provide some different. They are able to change the behavior of the neurons.
Is that sent as a wave or a pulse or a voltage? Or
that's the next slide. Okay, let's start with this. How does the signal processing work in the brain?
Transmission.
It's a combination of chemical and electrical processes. At the synapses here, typically there are ions, so there are some chemical processes which release ions, and then ions move into the cell here. So this is the dendrite, so the input of the system. If we think of an information processing system, has input, processing unit, and the output. Then all these small here are the inputs. The processing happens within the cell here, and the neuron only has one output. Now, how does it work? What you can see, I know there's other neurons basically attach these dendrites. You can create network. I will show you a picture later. And then, when those neurons send information, ions move from one neuron either directly into the second neuron or by some biochemical processes. But for today, let's just talk about electricity. So the brain, the signal processing within neurons is a bioelectrical process. Electrical power. That's it. The ions, they basically move the cell body. There they are accumulated. It's like a dam, you can imagine. Collects all the water, and then if the dam breaks, all the water exits. It's very similar. Maybe not a nice example, but it's a very similar process here. So once a specific threshold of ion concentration, electrical currents is reached, then here a gate opens and all the ions move out, moving ions, electrical currents. What's very important are these oligodendroids. Oligodendroids here. They create something which is called the myelin shed, which is basically an insulator. Because the brain is surrounded by liquid, fluid, and these insulation makes sure that the information really gets carried over longer distances. Without information, without this, you can imagine, like, cable into water, you know what happens. No, not the best idea. And these astrocytes, going back, because today we will talk about astrocytes and about neurons. They can change some of the electrical properties. It's like hormones. So there are different components who can change how those neurons here process the information. And by process information, again, we just mean which and how many ions flow into the neuron. Animation. How does this work? Again, this is an image of a neuron. This one here is the cell body, basically the one who integrates. These are all the dendrites, so this is all the input. And here we have one output, the axon, but this spreads and connects to thousands, tens of thousands. Hope you can see it from here. So, and now if I put a probe and want to measure the voltage at different levels, so if I want to measure the voltage here with the red dot, which is the red curve here, we see that some ions flow into the cell body here. Characteristic. If I put a probe here, I will see a slightly different curve, but a little bit later, so the x-axis is time. Basically, see that different currents flow into the ion. They are integrated, like the sun. It's really a simple integration. And then when a specific level is reached, which is basically 30 to 40 millivolt, then this gate opens and you see the information propagating through the axon here and connecting to thousands of other. It's analog processing here. It's integrating. Here's the threshold, and if this threshold is exceeded, open the gate and all the ions, so the current flows. A very simplified way how information flows in the brain. Now, if you have a look at the brain, just to give you an idea, this is a recent image where they did from 1 cubic millimeter brain. You see it's quite crowded. A lot of different cells. But if you just imagine the number, so in 1 cubic millimeter, there are about 57,000 neurons and about 150 million synapses. Synapses are the contact points between neurons. Imagine this network. If you do now some theoretical calculation, we have about 850,000 meters of cable in our brain. Because the cable or the dendrites and the axons is just to collect the information and transmit the information. Just to give you an idea, it's really tough to understand. Easy to understand, but to really comprehend. And overall, we have about 68 billion neurons in the entire human brain. So it's quite a huge number. And these numbers are probably equally wrong because next year we will have better methods and then we will see whether this is overestimation or underestimation. But that's science, you know, we need to learn to adapt. Okay, so this is just to give you an idea about the brain. Now, going back to AI, this is a picture from a paper where they tried to develop the perceptron, one of the first, actually not tried to develop, proposed one of the first neural networks, or artificial neural networks, based on the visual system. So this here should be the retina, and in the retina there are a lot of sensors which basically process the incoming light, and then the neurons by the optical fiber they project into different layers through the brain. From initial signal processing where we try to extract simple shapes, then maybe there are some association areas where you try to put those different objects together, which then at some point maybe you recognize is a horse or a cat, or in this case, an X. Maybe this person is playing tic-tac-toe, which then at the end leads to a decision here. I need to raise my left hand and maybe put down the next piece, you know. But the point here is, there's a collection, almost in the retina at least, it's really nicely arranged topographically, sensors which project along different layers. And you probably have heard about deep neural networks. Deep neural networks just means a lot of layers. And if you heard about convolutional neural networks, these are specific filters which really work nice on data, which can be arranged in a matrix, because then the information, adjacent information, is somehow relevant to make a decision. This is what they kind of simplified the system. And if we now think, what is this? If we think in terms of mathematics, it can be seen as nothing else as we have different inputs here, with different weights. So if I multiply input 1 with weight 1, and then I integrate it, it's weight 2, input 2, weight 2, and so back and so forth. So this means the output at the end is nothing else as a function of the sum of the product of all these different parameters. Here that language models have 60 billion parameters. These are the parameters we are talking about. Yeah. Structure, however it's structured. And of course, when I say large language model, they don't use specifically this structure, but just to give you an idea, these are the parameters we need to identify. This is quite challenging. Okay. And now we go to the computation. We're in the BCS. We're like digital logic and gates. And now, in reality, however, our computers, they work with logic gates, with memory. So basically, what we did in the brain, what we abstracted with mathematics, is implemented in a completely different environment. Again, so we already have 3 different levels of abstraction, if you want to call it. Some of the main gates, because we will see them later again, is the NOT gate, where basically, if there's no signal, this gate inverts it, for example, or the NAND gate. So AND means both have to be 1 in order for this gate output to be high. If I invert it and make a negation. Oh.
You inverted it.
Then, yeah, NAND gate. And these are just some very simple basic logic circuits which represents memory. This can store 1 bit of information, and computers are basically standard digital computers, I need to say, are based on this type of. Okay, so now this was a long introduction, but I hope we are all more or less at the same page now. And we all agree that artificial intelligence, what we use at the moment, the digital version, is very useful. However, there are some challenges, not especially if we think about silicon computing. Integration or miniaturization is reaching some limits. The energy demand to run a large language model is quite high. Even if you just ask, please improve this sentence, you consume quite a lot of energy. The heat dissipation is also very high. The more we integrate and the more we use this machinery, the heat must go somewhere. Typically, it goes into the ocean, which means the ocean will get warmer. Manufacturing complexity, somewhere we have to build them, and there's some material limitations. So this is just the silicon aspect. Then the general complexity of AI. We always mention language models. They work. Why do they work and how? We don't have so much clarity. We understand small components, but how altogether, that's quite difficult. Some say they know. I would say the majority is at least honest and says it works, but we don't necessarily know why.
Your informal prompt, of course, would get the wrong answer, because the prompt assumed that there was something wrong with the sentence.
Yeah, you're the language expert. I'm not. I'm an engineer. Okay, but I guess this is some of the challenges. So we all need AI. We all want to do AIs because there's a lot of benefit, but at the end, it's a lot of energy demanding. It's a lot of feed. There's a lot of challenges if we think about the crisis which is going on at the moment. So let's go back now to the brain. Do some calculation, and according to this human brain project, calculation is that the brain performs around 10 to the power of 16 operations per second per watt, yeah, which is 1 million times more efficient than the modern supercomputer. So it's really, really efficient. Even if this approximation is wrong by 1,000, it's really quite efficient. No? So of course, instead of understanding how the brain works, creating mathematical models, bringing them in digital, why don't we use the brain to do the calculation? And this is the presentation of the topic I would like to talk to you with you today. So how can we train neurons to do specific things?
Wow.
Oh.
Oh my God.
Yes, now the fun begins. I just try to prepare you.
By the way, your half-hour test will be waiting for you as you.
Yeah. Okay, so how can we do this? First, we need to culture neurons. No, it means we can use biological tissue or stem cells, mix them with some specific chemicals and agents, and then neurons will grow. This is how neurons grow in our body. No, everything is originated from stem cells. So we can now grow neurons. Then we need to stimulate them somehow. Now we know they work with electrical currents or chemical. So let's stick to electricity. So we can stimulate them by injecting electrical currents. This also means we can measure what they are doing by using electrodes. And then this is how we learn. We need to create feedback loops. I'm not sure if you remember when you learned to ride the bike, you tried it once. You tried it the second time, fourth time, and then at some point. So this is this closed loop. You try and you learn. Same at university. But hopefully you don't, yeah, anyway. And then why is this working with the feedback loop? Because the brain is really plastic. So it doesn't mean it's can take all different kind of configurations, but it adapts while you learn. It's also a good property. Because last time I talked a lot about patients who have physical disability or stroke. This is why stroke rehabilitation works, because the brain is a little bit plastic. So this is how we can train neurons to perform or behave what we would like to do. Now this is an experiment published 2002 in adult and from Cortical Lab. We talked to those guys, they work with us. Very cool. What they did, they cultured 800,000 living neurons in a dish. What you can see here, these red dots, I hope you can see them. These are electrodes. And they divided those into motor regions and sensory regions. Like the brain, we also have areas where we basically project to muscles, and we have some areas where sensors from our muscles, the periphery, project upwards. And then they created the Pong game, so a computer game. And then what they did is they connected the neurons here with the Pong game, turned the machine on, and this neuron conglomerate learned to play Pong in a few minutes. But why did it work? That's conversation before. Neurons like to be very energy efficient. So if you give neurons a lot of noise, they would need to create a lot of activity. But you can imagine if there's a lot of activity, they would always fire, and that's not what they want. They want to be quiet. They are like good students. They like just the minimum effort, maximum satisfaction.
How did you connect them?
Electrode. So this is not my work, just to be clear. But we start now doing this. I will show what we are doing. We finally got this machine. That's why I'm so excited. No, but here, so you can imagine it's a dish with all the neurons in there. Here there are some electrodes which you can use to measure electrical activity. But at the same time, you can use these electrodes to stimulate electrical or inject currents. This is how you combine them. Now, these electrodes here to a computer, and in this case, these electrodes here is like the left and right button. You can imagine from the Pong game. Then This is the virtual, this is the game. And then some feedback from this game is simply feedback to the neurons here by electrical stimulation. So you create a virtual representation of this, which corresponds to current or active.
So you make it noisy while it's not.
Noisy is
it
bad.
Tries to, and then it tries to get the
Exactly.
back to the ball to quieten it down.
Exactly.
And it knows if the bat's not at the ball, it's noisy. As soon as it gets near the ball, it's less noisy. So you're training the noise from the circuit. So yeah.
Because these are cells, they don't have a
Yeah,
concept
remember.
like I give you cookie or candy. They
Rather
don't.
than carrot.
Exactly. And for this case, and again, this was the hypothesis, and again, not my hypothesis. But by managing the energy of the neurons, because this is what biological systems try to do: conserve energy, not waste energy. And it worked. Quite remarkable.
So was this biological brain tissue or synthetic?
This was, I think they used human and mice, so they used different cells, but it's human cells and I think mice cells. One part is it's neurons, and then the question is always what's the not the easiest way, but the most efficient way to. And of course, one thing I did not discuss yet, the downside of this, we need to dispose of all these materials because those neurons will, like all cells, they will die at some point. No? Anyway, that's a different story. This is the science part. First, let's see what's possible, because if we know we can create neurons and we can train them in a very efficient way, tasks which otherwise on a silicium computer takes you, I don't know, days, months, years over this. And also the costs are quite, cheap. They just need a little bit of sugar and energy and yeah, and room temperature. We don't need super cool down rooms. And so from this point of view, there's quite a lot of savings already if we could control this. And now we know we can train them. We still need to learn a lot more on how to do it more efficiently, but at least now we know, okay, we can do it. Now, what if we, so this is one thing, but now what we need to do, because we talked about brain-computer interface, and this is something for Darling, how about we connect those brain tissues, cells, with the real brain? And this is what this experiment did. In the animal models, in the mouse, you create a stimulation unit, you embed some neurons here, and then you basically create or work on a protocol so that the axons grow where you want them to go. Because the axons is basically the output, and this needs to connect to other neurons. This is the big thing they showed. This thing from ETH, I think, showed that you can do it. There's a kind of microfluidic guidance where you put a kind of a cage around the axon, and then you guide it where it should grow into. And in this case, it grew into the brain of an animal. And if I now stimulate here, the animal will do whatever it's connected. Quite fascinating.
Creating cordyceps.
Is this like what's being used currently to help people who are blind or deaf?
No.
Not at all. Okay.
This is really. I mean,
The interface.
It's all very similar. Again, if I put this electrode here close to the visual cortex or close to the retina and stimulate, then people will also start seeing again if the optical nerve is intact. So the technology is always very similar. The difference here is that we can train something here and then put it in the brain, which is a different concept than bypassing what is damaged. And the big vision is I can give you, I know, I tell you later what the big vision is. Okay. This is another study, quite remarkable, which really shows that we can do it. So we really can create technology where we embed neuron, which then grow and connect to real living tissue. Next, and this is the world of the biohybrids. So biohybrids means we combine something which is non-living. I don't know, viruses. Sometimes viruses are used to inject some genetic material, which then goes into the cell and releases it there. Or we have here technology, humanoid robots, computer, you name it, and then we combine this with bacteria, the brain, plants, you know, animals, living systems, and by combining this, this is I think the big next step to help us overcome many issues. And great, so something for Darlene to have even more fear of what could be go wrong. But you know, you can use a knife to make some delicious food, and you could hurt yourself. You know. So of course we always, and I want to emphasize this in this area we always use the highest standard, ethical standard, because it's really crucial, especially working with patients. You know, if the brain is the only thing left, you don't want to mess around with the only organ. So it's really an important topic. But yeah, this is the word of biohybrid. So hopefully now you have an understanding what biohybrid means. Now, what is synthetic biology? I just try to disentangle the title a little bit. This is where we create new biological parts or devices. So we could use genetic engineering, for example, to create cells who do like computation, you know, act maybe like logic gates. Or we could design biological circuits. Imagine we can design specific neurons, and instead of training them, because at the moment we still need to train them, and some problems might be easier to learn or not. Like every one of us probably learns writing at some point, but it will take different times and different ways in order to be really fluent with languages. So this is the variability. But imagine we could create natural neurons, and design neurons, and design the function. Very cool. And of course, you can imagine all the applications. Not just medical. There's so much going on with environmental cleanup, biofuels. There's really a lot of opportunity. And if we now combine this with AI, then we have synthetic biological intelligence. So we create organisms which we can either combine with lithium AI, or we can use it to create something intelligent. And this is, I work with Michael Dutt, so one of the names at the first slide. Imagine now you have here some cell cultures, and we would like to create different logical operations, or to create different logical gates from the cell cultures. Now this was 4 years of work, just to give an idea. It's not really quick, but if you find a gene and you understand how to modify it, and then you find different compounds, so different molecules who basically change the behavior of the gene, then we can design cells which react in a very specific way in the presence of a compound or not. And in this case, some reinforcement learning was used here to understand the level of the compound. It's quite tedious, and it's quite difficult to understand. Therefore, we're no longer doing it because it's much more fun to work with you. But it was very important. So the concept is as follows: we have different inputs, so we can have cells which have a specific gene modification. And if we have this gene, and this gene has this modification, and we add this compound, then in this case, astrocyte cells, and astrocyte cells, they are not cells who can do active signal processing, they're just cells. That makes sense? Then they suddenly increase the calcium. So they open their calcium gates. And then by measuring the calcium, you can see what they did. So if this is available and this compound is here, high calcium level, if this is 0 and this is available because it's an AND, low calcium level. So but by mixing and matching the genes and these compounds, or in this case, you can create different logical functions. They don't work now like many of you already have a background in electronic engineering or digital, so they don't work like this, but the concept is the very same. Just to give you an idea, so in different concentrations, how this look like, time 0, and then after some time with the small 25 micromoles, of this compound, you don't see a lot. I hope you can see it. And if you have higher concentration, you see more dots, and these dots who light up, this is the calcium. So it's conceptually working, but it's quite difficult to comprehend because it's a different kind of signal processing. So let me just go back to the classical biocomputing, where we because what would be really ideal to have is we use all the combinatorial logic, all the state machines, Turing machine, all the concepts we have, and we transport them to biology. This would be really nice because we have so much evidence or so much understanding about this, you know, decades of training. This is some work we did, not in real neurons because we just now got all the devices, but this was with simulation. And just for you that you're aware that there are different models which we can use to understand different properties of cells. And the Hodgkin-Huxley model is the most defined, the most specific, but it's also computationally very expensive. So like I will show you then the Synopsis model, which is realistic, but very computationally effective if you want to understand or simulate different firing patterns. The firing patterns are those active. So depending on what we want to do, in a simulation, again in silicio, so sorry for jumping between domains, we can use basically the right tool for the right type of analysis. Like this Itzekevich model, it's just a set of differential equations. Typically, I had to include a differential equation just to see the reaction of the audience. Oh. Yeah, okay. Maybe it's a timer. I'm over time. So basically, the voltage, which we have seen before, the probes, you know, which propagates as a function of time, it corresponds to this equation, 0.04. The voltage squared and the voltage plus 140 minus u, which is this equation here, plus I, and I is other synaptic currents who flow into the. It's a really simple model, and this has a few parameters where basically you can define the shape of this action potential. So I have a few parameters where which I can tune to represent different types of neurons, and then I can take this equation to simulate how spike progression would work, how the spikes would propagate along the network. I see many PM, probably not the best time to discuss about this, but it's more or less clear. So it's use this equation to understand and see how the action potential propagates over different neurons and networks. Now, because there are many smart people around, and some already showed that by strengthening or weakening specific synapses, so the I in the equation before, we can create neural networks who work like logic gates. So I can inject an action potential or no action potential, and then maybe the neuron acts like an OR gate or an AND gate. This is a little bit more complex, but basically, you can also show that the gate can change functionality over time, which makes absolutely sense. But then another very important part, again, we see astrocytes are very important. If we have synapses and we have the astrocytes, they can change, or we know that they change the behavior, how neurons process information. So by influencing what astrocytes are doing, we can also change some properties of the signal processing in neurons. I see from the face, woo, quite a lot. Anyway, pictures. So we have here, these are just different neurons. So again, there's not one type of neurons. We have thousands of different types of neurons in our brain. And they all have different shapes of, well, all have the same function. So they integrate and then fire, but the timing and the amplitude, all is a little bit different. Also the speed. So the maximum firing rate is the quickest neurons fire with 1 kilohertz. Typically, it's 500 hertz. So signal processing is not as quick if you compare it again to modern. So if we now combine different of these neurons, one neuron provides one input, this is the second input, and if we just put them together, And based on the simulation, this behaves like an OR gate. Combine these two, also behaves like an OR gate. If you want to see where they are, there's some different axon cells. Yeah. Just in case you know what this means. For me, it's just name. Which is quite nice. But again, how does this work? Like we have two inputs, input 1, input 2. It's an AND gate. Then if both inputs are 0, also the output it should be 0. If you have an OR gate, the output also is 0. If we have one input 0, the other one 1, and it's an AND gate, the output is 0. 1, 0, output is 0. Only so if both inputs are 1, only then the neuron should fire. And this is what you can see here. So let's say this is time. There's no action potential. There's no action potential. So this neuron here doesn't fire. Then we have an action potential. There's no action potential. You see a little bit, but the neuron does not really fire. No action potential, action potential. Both action potential, then also this neuron fires. So just to give you, so the information is encoded in the frequency. They behave, it's a computer model, yes, I'll give you this, but they behave like digital gates. And of course, some analysis was done. This is really nice if it's slow and steady, but what happens if the frequency increases? And what you can see is that the higher the frequency of spikes, it starts here from 0 up to 200, then the accuracy of this gate goes down. So it no longer works really, really well, which we can expect. Yeah.
I'm starting to lose you a bit.
Yeah.
Well, are what you're saying is the brain represents classical computing in terms of AND or gates, not some form of multi-state quantum light.
No. Yes. Yeah.
So, but we're mapping classical computing onto biological materials.
Yes. Because if we can do this, this is just more energy efficient.
Yeah.
Really straight. And it's a model again. The next step is to do this in the lab and show it's working. But again, there's already evidence it's going to work. It's just we need to design it in a way so that it's stable, because it's not helpful if it works from 5 minutes. We would need it to work for extended periods of time. Anyway, and so what I try to say here is that, of course, if you can imagine, if this frequency here increases, because cells are not computers, there's always this variability, and cells also fire spontaneously. So it's a little bit different, but I don't want to overcomplicate it. The point is just, even if we increase with the spike rate, even without manipulating a little bit, it still performs okay-ish. Maybe no longer here, 30%.
Is there a difference between the performance of neurons and cells between different parts of the brain? I'm thinking particularly of the amygdala and the frontal cortex, which are quite different, have quite different functions. And I just wonder if the cells are different because of that.
Probably. I don't know where the causality goes to.
That's different matter, isn't it? Grey matter and the
Grey matter are
two different.
Gray matter are the cell bodies, and the white matter is the cable. So the myelin shed, which I described before, this is basically just the isolation.
The amygdala is the oldest part of the brain. It's the top of the neck, the stem.
Yeah.
That's the bit that.
No, the cells will be
That's
different.
the flight or fight portion.
Yeah, but if I understand you correctly, the question is, do different systems have different neurons?
Yes.
Yes. They all work similar, but they are different.
And so the question is, which type are you modeling?
Here we use these different types. These numbers are different types of neurons.
Okay.
Different cells.
Different cells.
Okay.
And you just pick the combination, which is which is giving you the function, pragmatically speaking, you want to have. Again, this is in the model. Not that it's not cool, but I just want to make sure it's simulation. And so if the firing rate is really slow, so if it's below than 70 spikes a second, then the performance is, the AND gate still in 80% of the time works like an AND gate. The OR gate. Yeah. It's a little bit worse.
I'm not losing something in terms of actual computational potential by being digital Boolean logic onto something which is a sort of hybrid analog digital.
Yeah, this is just exploring what could be done. Does it make sense? Probably not. But so,
well, as you
not
said,
if you want to be
it's for energy efficiency, but in doing so, you're kind of losing some of the computational ability initially, at least.
yes.
Yeah.
What size are these then compared to like a 2 nanometer chip? These are much smaller, right?
This is just a model, but the neurons itself, they're much smaller.
Yeah. So it is a whole game changer really from that point of view.
This is one question which I tried to figure out, because I've showed you this really nice how many neurons are in 1 cubic millimeter brain. I don't know how many transistors are in 1 cubic millimeter semiconductor. Maybe this would be a comparable.
Yeah, there was we saw something a week or two ago which said that a large language model is somewhat less than the capacity of the brain of a fruit fly.
Yeah, it just typically has a few
In
billion.
terms of physical size.
It's very directed, I think.
Yeah.
Neurons themselves, they're in the millimeter scale.
Yeah, micro. So there should be a picture. I hope there's the scale. So I show you some pictures of astrocytes because we did some experiments already in cells. But yeah, what I really like is the engagement and excitement, and I understand why I'm so excited. There's so much potential in this. So much can go wrong. We just need to figure out what's the right way to do. And mapping digital into neurons, maybe not the best and most intuitive way, but maybe it's one way for sustainability until we figure out, or maybe never work. I don't know. That's the beauty of science and the risk of science. But it will work. Anyway, so now the question is, because you all ask very, very good questions, and what do I do now with this? Is this good for anything? So let's talk about epilepsy. Let's assume we have a microcircuit. I will show you a few neurons which form a microcircuit, and if we can introduce epileptic spike, some spiking, which is basically comparable to epileptic seizures. Could we not use some logic gates, for example, to stop it? How do we do this? We potassium and sodium, just if you want to know, there's the paper, we can have a conversation later. But the important part is, if we have such a network, here you have different neurons and you see the different connections. So this is a small word representation of a network where you see the different areas of the different neurons and how they are connected. So you can imagine this is a network. What happens if we put in this network somewhere our logic AND gates? Basically, what happens if we do something like this? If we have these different cells and we connect them with AND gate. Why AND gates? Because AND gate can act as a filter. So both have to be on to firing. And if you have many spiking neurons and they don't fire synchronously, then this will break the spike. That makes sense. So this explains it. So here we have different cells, which when you start the simulation, okay, they fire based on a Poisson distribution. This is what neurons do. And then we manipulate a little bit the ions to create spikes. You see, suddenly it starts spiking. And here we have this classical seizure. Then what you see, once this gate here, when this is integrated, as soon as it starts seizing, it will shut down. So maybe it's not clear, you don't see it, but even if the firing rate is higher, so even if the gate is not really working well, just being able to filter it would allow us to, if we can inject them, but we have seen that we can combine train neural networks and combine them with the brain in one of the studies. So if we can create now these neurons with this function, maybe this could be one way. So for people who have epilepsy, but they are drug resistant. Imagine what's even cooler. Oh no, that's later. This is just the beginning. Then it gets no cooler, and then I stop. So this is some other simulation. This is we used. I don't know again the type of neurons, but I will look it up. But we used this Itzekevich model, and what we did, we created inverter and a NOT gate and NAND gate, because if you remember, all components can be created with NAND gate. So if we can design neurons who behave like this, we can design all kinds of different. Again, if you look at the pattern, they behave. And what we did here is we just tried to calculate the energy consumption. So you see that how the energy changes over time. Because if you want to make the claim it's more energy efficient, we should somehow estimate. We can get more complex. Suddenly we have latches working. We have gated latches. And we have D flip-flops. So basically, which we can clock. So by creating in simulation, okay, exploring the parameter space, how those neurons would work, if we are able one time in the distant or not so distant futures to create neurons who behave like we want, we could use the technology we have now for digital technology, put them into neuron. Imagine you design it and then you 3D print it. Imagine you have epilepsy. You go to surgery, the surgeon removes part of your brain, 3D prints it, close it, all done. This is what we want to achieve, all done. So this is our 3D printer, which has different inks where you create some scaffolds, because neurons, they are quite tricky to work with. If they don't like the environment, they decide to die. So we need to create a really good environment, but also what we need to do if we want to design circuits, now whether they are, digital or whatever form, if we want to create a specific topography, we need to find ways on how to encourage them to form these networks. And this is by creating the scaffolding, which can look like this at the moment. It can just be circles, just this kind of matrix, and then if we stack them, we can create 3D models where neurons basically. Oh, maybe I forgot to say, we print this. It's a kind of a algonet. Then we harden it, and then we put neurons here. And then since neurons like the surface, they will basically, we need to encourage them to work in the right position and connect. And then we have a network which looks like, which is the network we would like to have, or we want to have. Then we can do this in 3D. This is just some first experiments. So this is just the scaffolding, and here is on day 2. Again, we can print fixed and fully formed 3D brains. Nature still has to do the work. We can speed it up, but you put some cells here, and then what you see after some time, here's day 17, they start to group together and form some organoids. And organoids are basically like small circuits, which like the brain, each brain. So this is some of the work we are now doing. Of course, what you also want to do is this these shapes look a little bit weird. This was just the first test, but of course, if you want to have more complex stuff, we're not trying to have a 3D model of a scaffolding we want to use, and we print it, and then hopefully we have all the neurons who grow where we want them to grow and to connect how we want them to connect, because then they will perform the function, which hopefully we trained them or designed them to do. So this is the end of my talk, but it's just the beginning of what we try to do. So I hope you got a little bit an idea of what biohybrids are, what synthetic biology is, where we can design cells, organisms, and of course the benefits are many. We can really have very precise intervention if we really manage to grow axons where we want them and where we need them. Biocompatibility is a big problem, but if we have materials like neurons, they should be biocompatible with other neurons, and hopefully this has a big benefit in the future for implanted technology. Of course, medicine. Or imagine you have this, we create artificial neural network, natural neural network, like this brain, and you connect it to cancer cells. And then they start to understand how the cancer cell works, and communicate with them and learn much more, because those networks, they learn in real time. Not like where we collect a lot of data, a batch, and then we train it and then update it. No, those, it's in real time. That's the true performance. And then of course, advancing computing and AI with all the different things which I try to show you what we think. Hopefully, some of them will work out in the not so distant future. Therefore, I hope I'm not too optimistic when I say 20 years. Probably am. But this is some of the new exciting things we are now working on, also gaining momentum with more students and finally having the right hardware. When we got the last piece where we now can measure an interface with 69 neurons, quite excited. Thank you very much for the interactive session. Sorry, for the interactive session. If you have questions, I'm here. There was one before.
Hi, thank you. Yeah, definitely impressive. Thank you very much for your talk. I'm curious about your view on even quantum computing capability to process simultaneously, comparing with the binary system. Would this improve the efficiency in digitizing waves in your case?
Quantum, difficult. As soon as it's proven it's working, yes. But at the moment, there are so many things which are still not well defined in quantum computing as well. So yes, of course, if we can manage quantum computing, and maybe we can learn some of the effects here or combine them, or maybe it's not even needed if we fully understand and have quantum computing. I don't know. Yeah, I feared quantum computing is. You had a second in that.
Given that neural processing is inherently pulse-based, and you don't have steady state outputs, what sort of challenges does that present to you?
Yeah. So the question is, did you hear the question? If not, basically, the question is if there's no steady, neurons fire anyway, I guess. That's what I mentioned. So even there's no signal processing is going on, neurons will fire because they fire according to a specific distribution. And then there are some delta changes within this. Yes, it will have an impact, but we can try to so since we managed to synchronize some of these neurons, and if we can design design these latencies into the circuit, then it should be manageable. Yeah, it's all the questions we need to address, but yeah.
Brilliant presentation. I learned a lot from you.
Thank you.
I would like to ask you about the ethical ground of this technology. All you said is fantastic. You cure people, epilepsy, dementia, Alzheimer. What if people use it in an unethical way? For example, athletes, they can do bring chips to cheat in the Olympics, to make them run faster, swim faster. And maybe people may implant the chip to their children, they become smarter in the class. How do we strike a balance between people who have money to make themselves superhuman, as opposed to people actually ill and need the help to get better?
Yes, this is the £1 million question. No? I mean, I think we just need to be honest, and I think the current economic system prevents, forces this to happen almost. No? So we need to just change how we behave as humans, because if we give all the power to AI, and if money is basically who gives you access to this, then by definition that's going to happen. And it happened already. It happens already 20 years. We talk about AI. If you don't have a good curriculum, or sometimes you don't even know why you get a credit card or why you don't, because someone is making a decision, and so this divide is already here. But your question is, how can we try to prevent this? It's just having an open conversation and keeping on having this conversation, because what you mentioned, this is true for many technologies, not just for this here, this is a very personal value, because it's the brain and it can really transform how people live, especially the one who have disability, but of course it can improve the life of others. Just be
the Olympic medal.
Again, we just
To make us obsolete. So considering the inequality and it's just
this is a completely different question whether we are still needed. Let's not go there.
Sorry, in addition to what she said, ethical, supposing like trying to cure a problem like epilepsy you mentioned earlier, and something goes wrong. So the ethical aspect of it, what are you going to do in order to correct that part? Or do you reverse it?
And the legal aspect, I mean, there's a lot in this community, there's a lot of conversation. I mean, this maybe not yet, because it's still in the very early stages. I work in neurotechnology and brain computer interfaces, where we have regular meetings about ethics and try to involve and be engaged with standardization and with the government, because there have to be some clear guidelines, and people hopefully stick to it. So at the end, it's always, not everyone will always stick to it, and there will always be this one person who maybe doesn't do it. But we just need to have a conversation and agree. And if we don't agree and don't have trust in each other, then it's very difficult. No.
I think, in my opinion, that where the government policy should come in.
Policies must come in, but of course, it's like with sport or doping. Policy is always late. So
like just what happened in the news yesterday, and I heard it this morning. They gone to the hospital and they said to them, and the user is one of these devices they use that they confirm that the baby is dead and that they need to do operation. The following is in the news, is very just recently, yesterday, and the following day, I think that's happened in 2023. The following day, the woman delivered, and a device from the hospital has confirmed the baby is dead. So can you imagine that kind of all the technology that comes in? That's the advantage aspect of it.
The difficulty is individual. If this happens to one person, it's very horrible. But if in average we are able to have less deaths, then this is good, even if it's bad, if you know what I mean. So
cost versus benefit.
Sorry?
Cost versus benefit.
Not cost.
It's a moral cost.
We don't. Yeah. We don't know.
The good outweighs the bad.
Getting back onto the subject, right?
Yeah,
that scenario.
That's right.
Is the devices they use to test if the baby is alive, and for no reason saying that the baby is dead, and it's not a miracle. Something is wrong with the devices they use. That's confirm if the baby is alive in the.
This is, for me, this is the same like if you buy a knife and the knife breaks and you hurt yourself. It's a very similar.
Talking of a woman being.
Yeah, but I know, but if for these very easy cases we don't have regulation, you can imagine how difficult it will be here. Therefore, I'm saying we just need to have the conversation going. Is there a solution? Because the development is so quick, and different countries have different regulations where you can move at different speed. This will always be a problem, but we just need to agree. And once we understand the risks, legislation should be put in place, standards should be put in place, but bad things will always happen, no? And I know my kids also have, but I definitely I'm saying at a personal level, it's difficult. The same for patients. The patients who volunteer here will not benefit from this technology, no? But they maybe work now with us so that in the future, the people, it's a very similar, I'm not sure if I get the point across correctly. It's very difficult, but sometimes we will not have the benefit, and mistake happens. But if mistakes happen, we just need to own it. If we make a mistake, it's my mistake. No, but I don't know then what the consequences are depending on a product, because this is still research.
Just to get back to the, obviously you've broken it down so everything's really simple. That's like a wrist chip where it's all ands, ors, nors, and gates. But we're not like that, are we? We're like a sys chip where we have we'll have a group where it does a complex, our thoughts and everything are more complex. Everything's not noughts and ones and ands and ors and nors, is it? So we haven't just managed to get into that level of detail yet. This is just us purely just being at the
This is
the outside.
This is just trying to understand what we can do and trying to understand where we need to invest time and develop technology to be able to answer all these questions, And I know this, and again, I told you, I go outside my comfort zone because this is really, really new and many concepts are still, they are clear one day and then you wake up the next day and it's like, I have.
Well, in a cis chip, we can do one operation, does a load of operations, isn't it? And we've had cis chips for years, so presumably there's something in their brain that does a similar.
The brain is all parallel, no?
Yeah. Okay. Yeah.
It's thousands, millions, billions of networks which all can fire whenever they fire.
The result.
And then you integrate, and at some point there are some mechanisms which maybe makes us conscious. But yeah. There's so many questions.
There's a model of cognition, which is sort of modeled on computing, and we look at it models short-term memory, long-term memory, information processing, and I don't suppose you have the answer to this, but do you suspect that there are different types of cells that do that, or different types of activities with those cells that do that? In other words, long-term memory is possibly just sitting there, not doing anything, whereas information processing, like we're all doing at the moment, is active. So have you got the idea of passive versus active?
Yeah, there are different theories where some parts of memories, some even say it's not even just in the neurons, but in mitochondria. So there are many different theories where the memory can be located. No? What makes most sense for me at the moment, it has to be, because the neurons are always firing. So if we just stick the neuron, it has to be in the network activity. But I don't know what the
So it has to keep firing in order to stay alive. Maybe.
Yeah, but we have so many neurons, and you don't know when they fire together, so that they create this pattern, which creates this very specific behavior. Because if you have 80 billion neurons, there are quite a lot of combinations, and maybe you need some specific to trigger something. But again, I'm a computer scientist, so I don't have the answer. So there was one question there. Then
there is a question online, a very simple one to read. How far away are usable biocomputers, do you think? And I should add, what does that mean?
20 years.
I was just thinking, oh my gosh, yeah.
20 years.
I mean, as you have seen, the bomb is already there playing. If this is a biocomputer, no. If we talk about redesigning a specific function, there are still some. I hope before I retire.
So you're working on interface, yeah?
Yeah.
Last question.
People get upset. Two more questions.
You mentioned to create a gate-based systems through the individual cells. Is that completely not facility system because of one cell? Perhaps. And I have to learn software, artificial neural, only it's physics-based. The other system will be replaced. How do you connect?
Yeah. So the question was, if we try to create gates from neurons, but neurons will die, then your circuit at some point will be not working. Yes. That's going to happen. But first we try to understand if it's possible. So the model tells us yes. We don't know if we can create synapses or cells, real living cells who behave the same way. And if that's not possible, then the question ends there. But this goes back to the question before, is it a meaningful way to do it? I don't know. This is just one way to understand, because we have so much knowledge about digital gates. And if we have to start from scratch something, it's quite difficult, no? At the same time, the dish-brain experiment shows that if you're smart and understand the behavior of neurons and you subject them to white noise, then suddenly they learn quicker. So there are many ways to different pathways we can try to reach. What's the best? I don't know yet. So we just try different and see what's possible, what's not possible. But yes, it's a good point.
My one is very quick. You said it's a living cell, that's right.
Yeah.
And how long this living cell will finish the last?
Hopefully 1 month. Yeah, so at the moment in the lab, it's quite difficult because, cells are really tricky to work with, and we need really well-controlled environment. And I think our cells died about after 1 month or so.
So you have to 3D print it, or
Yeah.
how do you do?
We have 3D printed it, then move to life science. They have in an incubator, they cure them, and then you do some experiments, and then at some point it will die. But yeah, these are living cells, This is like happens in our body as well. But at the same time, the cells regenerate. So maybe there are other mechanisms we can trigger to regenerate some stuff. But in average, all the cells in the body are regenerated within a 7-year cycle. So 7 years ago, you were completely different matter than you are today. If the research is still. Afterwards, I guess he wants to.
I want to chop you up. Great. Well, I don't know how much of that you understood.
Sorry.
I understood my usual 10% of Ryan's lectures. So lots of things to think about. But I guess the main thing is that we are computer scientists and we're doing ever such complicated things. And we're moving into quantum AI and more tricky fields and so on. And it's all so simple in comparison with our brains. So the next time you're really impressed by the speed of computing and all that sort of thing, take a look in the mirror. Have a think.
That's a motivational speech.
Meanwhile, let's have a look at Reini, and please join me in saying thank you to Reini.